Okay, so I will be talking about black holes and how gravitational waves will relate to black holes, because it's a vague margin to see how these two relate. I got this presentation and synthesized it from Cardiff lectures and a lecture from Rutherford, Alperton, and various article sources. Firstly, you all know the guy, Einstein. He was the person who proposed the theory of special relativity and general relativity. One of his eureka moments was that if a man falls freely, he would not feel his weight. This has introduced the idea of perspective to him, and it gave way to one of his major groundbreaking ideas, which we'll talk about. So, firstly, the main idea was space-time. What space-time was that what we perceive as time is not linear. So that's like quite difficult to take into your mind, because all our lives were kind of constantly thinking about time going as like present, now it's the future, now it's the future, and things like that. But what Einstein proposed is that time is not actually something that happens continuously, but is actually something similar to like an object. Is more of a it can be of matter. So which led into the idea of fabric of space-time. Now, what this idea is that if you picture space-time as a sheet of fabric, is the general analogy, is that once you put in a weight onto that fabric, what it does is warps space-time. Now, what that idea is that, so it warps space-time so that the moment you are here, the time you perceive and what you feel as time going past is different to say if you were here. Because at this point, space-time is being warped by the massive amount of mass to cause you to have a different perception of time. Now, this leads into the idea about gravitational waves, because the denser the object, the more it warps space-time. And so, for these three examples, for the bigger object, there's more curves, and the space-time is warped more. So the actual density, the actual time perceived is longer. So this leads into the idea that time is relative, which once again is counterintuitive. One of the ideas that also stem from general relativity is that all laws of physics are constant no matter where you are. So one of the laws is that light is constant. This is one of the ways, and which we will talk about later, of how it relates to how we measured gravitational waves, which is the whole thing of itself. Just a prop to Herman Minkowski. He discovered space-time, not Einstein. With the gravitational effect, because it curves space-time, the explanation that Einstein gave is that because of the curvature, we experience gravity. It pulls us towards it. Okay, there's a little thought experiment to give you an idea of how time warps around us. Is that, let's say we have a car, and we shine a light. The car is going at, let's say, 30 miles per hour. So light being 3 times 10 to the power of, 3 times 10 to the power 8 meters per second, you think that you'd be catching up to light, so therefore the light speed is, the distance between the start of the light point is shorter. However, if we introduce a different object of much faster speed, you'd think you'd catch up to light more, but when you shine a light inside the rocket, But what actually happens, according to Einstein, is that you do not catch up to the light. It's more time warps around it so that light can be constant. So time is not constant, but rather light is constant. So can I just get a, is anybody lost? Because that's quite, yeah, okay. Don't worry if you're not, because it's quite complex in its own idea. Okay. With gravitational, how this relates to gravitational waves is that what happens when a massive amount of mass collides and then it sends, what would happen? So an example of this would be two massive, dense black holes colliding to become one. Now, one. What would happen is that they would constantly spin around each other, and I think it's about around the speed of 300 meters per second, 300 spins per second, which is an absurd number for like the size of the black holes. And this, when they collide, it'll explode and send a ripple across space-time. Now, what this, so it's literally a gravitational wave rippling through space-time. And how we measured this was through this experiment, like a large-scale experiment, LIGO, named there, and in America. These people, not that you probably care, so the actual experiment was that because they're trying to measure these space-time warps, what they do is, because they take speed of light as constant, they have a laser that produces a light that is reflected into two diffracted into two different streams of light that are a very long distance away from each other, and they will bounce back into the light again. And what should happen if no disturbances are found is that nothing should be detected as the light cancels out each other. But what happens if a gravitational wave occurs is that it warps space-time, so the actual path the light takes in space-time is different. So what this causes is a disruption which allows the detector to detect an actual ray of light, which we can put into waves, etc. And yeah, so they can actually put it into a computer to process, and it actually produces different disturbances. I believe this was a neutron star, and that was two neutron stars colliding, and that was two black holes colliding. What they also did, which was quite interesting, is that they put this into sound frequencies so you could actually hear the black hole.